Hi and welcome everyone to this lesson in our course for MATLAB. In this lesson we are going to discuss how can we simulate the series resonant circuit. Okay, so simply what does a series resonant circuit mean? In the series resonant circuit we will have the XL is equal to XC, and in this case when XL equal to XC the output voltage will be maximized. Okay, so the voltage across the capacitor and across the inductor will be maximum, and at the same time the current inside our circuit will be maximum, because the current in this case will be the supply divided by the resistance. So anyway, we have an example here for a series resonant circuit. Here what are we going to do? We are going to simulate this circuit. Okay, this example is from my own course for electrical resonance. We are not going to discuss this example, but we need this circuit in order to simulate it. Okay, so we have this circuit which is a supply voltage, AC supply 10 volt and angle 0. We have a resistance of 2 ohm and inductance of or XL equal to 10 ohm, reactance 10 ohm, and reactance of the capacitor is equal to 10 ohm. So they are equal to each other, and the resonant frequency is 5000 hertz. So here, since XL equals XC at 5000 hertz, so this is the frequency of our supply here. Okay, so let's start. The first step is that we are going to add all of these elements, then we are going to simulate it. Okay, so if we go here to our MATLAB program here, then we click new, then we choose a Simulink model like this, blank model. Okay, like this one. Now the first step is that we need what? First one is an AC supply. Okay, so here I'll double click here, then type AC voltage source. Okay, AC voltage source, and remember electrical specialized power system sources like this. So we have here our AC voltage. Now this AC voltage is 10 volt peak and angle 0. Okay, and its frequency 5000. Okay, so here double click here, so the peak amplitude is 10 volt. Okay, phase angle is equal to 0 degrees, and the frequency is 5000 because it is our resonant frequency. Okay, like this. So this is our supply. Second step is that we need to put a resistance of 2 ohm, XL equal 10 ohm, and XC equal to 10 ohms. Okay, so what are we going to do? Simply the first step, resistance. Okay, now you will see that we would like also to see the voltage across resistor, the voltage across inductor, and voltage across capacitor. So we can use something like this, series RLC branch. Okay, you can see this one. Okay, resistance, inductance, and capacitor, as we need here, resistance, inductance, capacitor. However, if you double click here and try to take the measurement, you will see that it takes only the branch voltage between this point and this point, and the branch current or branch voltage and the current. Okay, so what we are going to do is that we are going to divide this. So as you can see here, it is one block. So for example, if I say voltage measurement, okay, like this. Okay, and I would like to measure the voltage across resistor, for example this point and the other point here. Okay, you can see you can't do this, it is one complete branch. Okay, so what I'm going to do is I'm going to divide this into 3 parts. Okay, so we are going to here copy, okay, and paste, or control and drag, they are the same thing. Okay, so we have 3 branches here. First the resistor R, second inductance L, third capacitor C. Okay, now here like this, okay, connect the resistor here. Okay, connect the inductor here and capacitor. Okay, we can make it like this, rotate it, so we can say this and control R. okay, Control R to rotate, okay, or right click and rotate and flip from here, okay. Both of them are the same. So we connect this one here, connect this one here, and so on, okay. Now before we take the measurement, we need to add the values. So the first resistor is 2 ohms, so we'll double click here and 2 ohms, okay. Then we need the inductance, okay. Remember here we have inductance, okay, inductance. So here the input is L, or the inductance in Henry, not the reactance in ohm. So what are we going to do? You know that XL is equal to 2 pi multiplied by the frequency, okay. So we can take the calculator like this, okay. So we know that XL, which is the 10 ohm, is equal to 2 pi multiplied by the frequency multiplied by inductance. So in order to get the inductance, take XL and divide it by 2 pi multiplied by the frequency. So we'll divide it by bracket 2 multiplied by pi multiplied by the frequency of the supply, which is 5000, like this. Then equal, you'll find that our inductance is 3.183 10 to the power negative 4, okay. So we'll go here 3, okay, we'll type here 3.183, okay, okay, 10 to the power negative 4, okay. So to the 10 to the power negative 4, like this. So this is our inductance, similar to the capacitor. Note this one here, capacitance. You know that XC is equal to 10 ohms. So go back here, delete all of this. So we know that the capacitance, which is the 10 ohm, is equal to 1 over omega C, okay, 1 over omega C, or 1 over 2 pi multiplied by the frequency multiplied by capacitance. So anyway, it is very easy. In order to get the capacitance, it is first we will get the inverse of 2 multiplied by pi multiplied by the frequency, which is 5000, okay, multiplied by the 10 ohms, then get the inverse like this. So we'll have 3.183 10 to the power negative 6, okay. So we will have here like this, okay. Take this one here and paste, okay. So if you don't know where did we get the capacitance and inductance, okay, let's get back here in our course where exactly, okay, when XL equal to, you can see that XL here in resonance in series circuit, XL is equal to XC. So omega L is equal to 1 over omega C, which gives us the frequency, which is the 5000 hertz in our circuit, okay, which gives the resonance. So XL is equal to omega L, which is 2 pi multiplied by the frequency multiplied by inductance. So by substituting XL to 10 ohm and 2 pi multiplied by 5000 multiplied by L, so from here we can get the inductance. Capacitance XC equal to 1 over omega C. So the capacitance is 1 over XC multiplied by omega, okay. These two equations is the one which we obtained here in our calculations, okay. So let's get back to our first example here, okay, here. So let's get back, okay. So now we have resistance, inductance, capacitance, and supply. We should be at resonance, okay. So what I would like to measure is the voltage across resistor, voltage across inductor, voltage across the capacitor, and the current flowing through the circuit. So first I will use a current measurement like this, okay, to measure the current flowing inside our circuit. So first, the positive terminals representing the entering current. So here in the positive cycle or in the first cycle, the current going like this to the resistor. so it going like this, so it is a positive, then the output is a negative. Okay, so like this, okay, take the positive terminal plus like this, and the negative like this. Okay, so it means that we are measuring current flowing in the from left to right. Okay, so this is our current. Second thing, we need to measure the voltage across resistor, voltage across inductor, and voltage across capacitor. So the voltage is plus minus. This is the voltage I would like to measure, and the plus minus here and the plus minus here. So the positive of the measurement here and negative of the measurement here. So it will be like this, plus goes here and minus goes here. Similar to the same idea, copy, we need 3 of this. Okay, 1 for the capacitor, 1 for the inductor, and 1 for the supply. Okay, so it will 1 for the, sorry, not the supply, resistor. So we have here positive, negative, here positive. Okay, sorry, Control Z, take this terminal, this here, take the other terminal here. Okay, so we have here our 3 voltages and current. Now, in order to view all of this, we can use something which is called the scope. Okay, so we type here scope like this. Okay, so we can see all of the output waveforms in it. Okay, so first we will double click on it. Now, as you can see, we have how many inputs? 1, 2, 3, and 4. So we have 4 waves we would like to observe. So we'll go here to the scope, go to the settings here, and how many inputs? We have 4 inputs like this. Then click on apply and OK. Okay, so if you go back to the MATLAB, you'll see 1, 2, 3, 4. Now you have the first input like this, second input like this, third input like this, click and drag like this. Okay, so we have here our 4 inputs. Okay, nice. Now you have to know that when we do this, and you have seen one screen, this is one screen, so all of the waveforms will be above each other. Okay, so what does this mean? You will understand what I mean right now. So first we will add a block called Power GUI in order to simulate this circuit. Okay, now first you have to know that what is the frequency of the supply. Supply is 5000 hertz, which means it repeats itself every how many seconds? You will see right now, 1 over the frequency. So every 0.0002, every this time, we have 1 cycle. Okay, so I would like to have to simulate 2 cycles. Okay, so like this, and 0.04. So we have here the time is double of the periodic time, which means we are seeing 2 cycles. Okay, then we are going to click on run like this. Okay, then double click here. You will see all of the signals here. Okay, you can go here, right click, configuration properties. Okay, then click on show legend. Okay, show legend, then apply. Okay, you can see here the first, the yellow signal representing the current measurement, the blue signal representing the voltage measurement, the red voltage measurement 1 and voltage measurement 2. So what does this even mean? Now if you get back to the circuit here, you will find that this one is called current measurement. So the first signal here, current measurement, is the blue one, is the yellow one. Okay, the yellow one representing the value of the current of the circuit. Okay, the second one, which is voltage measurement, you can see here, if you go here, voltage measure, let's zoom in, voltage measurement, current measurement. If we go to the right here, voltage measurement 1, which is the voltage across the inductor, and here voltage measurement 2, which is the capacitor. You can see here voltage measurement 1, voltage measurement 2. You can also change this by if you would like to say, for example, current, you can say here current like this. Okay, then click like this. You will find that here when we update or run the simulation once more, it should be changed. As you can see here, current. Okay, you can see it changed here. Okay, like this. Okay, let's close it. Okay, let's run once more. Okay, stop. Okay, then run. Okay, then open the scope like this. You can see current. So we can rename our scopes as we would like. Okay, now here you can see that all of the signals are on the same graph. What if I would like to divide them into several graphs? How can I do this? You can simply do this. For example, we have here 4 signals, so we can divide them like this. Click this button and go down here to the third one, this one. Okay, layout, and then how many graph you would like to, you have 4 signals. How you would like to see? Do you would like to see like this, or you would like to see down each other, or I would like to see them under each other? So 1 2 3 4 like this. Then click. You will see, as you can see here, each signal like this, 1 2 3, each one is alone. So the first one is the current of the circuit. Now if you look at the current sine wave, which is, of course, since we have an AC source, so it is a sinusoidal wave. Now what is the value of the current in resonance? You can see that the peak value here is 5 ampere. Okay, so if you already know about resonance, you know that the peak current is equal to the supply, which is 10 volt, divided by the resistance, which is 2, gives us 5 volt. Okay, so if you know about resonance, 10 divided by 2, as you can see here, the current through a resonant circuit is equal to 10 volt multiplied by 2, or the supply divided by the pure resistance. Okay, giving us 5 ampere. Okay, so as you can see here, it is the same as you can see, and zero phase shift, it starts from 0 like this, similar to the supply. Now second one, which is the voltage across the resistor, okay, which is a second signal. You can see from 0 to 10 volt in phase with the current. Okay, 10 volt peak, because the voltage across the resistor in resonance, in series resonance, it will be similar to the supply. So supply is 10 volt, so VR is equal to E equal to 10 volt. Now going for the last 2 signals, one signal for the inductor and the other signal for the capacitor. If we look at these 2 signals, you will see that they are shifted by 90 degrees, or not 90 degrees, to be more specific, 180 degrees. You can see that here VL leading by 90 degree and VC is lagging by 90 degree. If you observe these 2 figures, this 2, you will find that they are lagging, that phase shift between them is 180 degrees. Okay, so now what I would like to do, okay, so here let's see the voltage. So you can see the big voltage here in this point is 50 volt. This is the peak of the inductor voltage. And look at the capacitor peak, it will be also nearly 50 ampere, nearly 50 volt. Okay, not exactly, because I am not putting the values correctly. Okay, you can see here that it is not exactly 3.183. there is a 3.18309 and so on, some factors also. Okay, so this small factors gives this a small error. Okay, so if you put the exact resistance, exact inductance and the exact capacitor, you will have the same exactly the same voltage, 50 volt and 50 volt. Okay, now is this correct, the 50 volt? Yes, if you get back here you will see 50 volt and 50 volt. Okay, it is 5 times the supply. Why? Because the quality factor of this circuit in the series resonance circuit is equal to 5, which means that when the voltage will increase, will be amplified by 5 times. Okay, so 5 multiplied by 10 gives us the 50 volt. Now if you don't know about resonance in general, I suggest that you go and see our course for electrical resonance. Okay, so this was a simple example on the series resonant circuit. Okay.